So this is the best rainbow I've ever seen. I was standing on a hill in McAlester, Oklahoma, looking off to the east, and there had been a really bad thunderstorm that had passed us, and now was to the east. We're looking at it, and the sky behind me was super bright. You not only could see a huge chunk of the rainbow, but you could see a double rainbow off to the side of it. So I have always been fascinated by this. Why can I see different colors? How can the sun be turned into different colors? And so far we've talked about how waves can carry energy. And one of the obvious ways that waves carry energy is sunlight is the primary source of energy for most things on Earth. So in this week of learning, what I want you guys to try to figure out is how light works, how light carries energy, and what the difference between different kinds of light are. One thing about light I suspect you already know is that what we perceive as white light, which is coming out of this light here, can actually be separated into what's called a spectrum. So here's a rainbow, and we can see the rainbow really starts with a very deep dark red, transitions into orange, then yellow, then green, then kind of a bright blue, a darker blue, which is called indigo, and later violet. So what we think of as white light is actually many different kinds of light mixed together. What physically is the difference between those different colors? So as we enter this unit, in distinguishing between different kinds of light, it's important we remember our wave speed equation. Velocity equals wavelength times frequency. Velocity is measured in meters per second, wavelength in meters, frequency in hertz, or 1/seconds. With this equation, we can relate these three concepts, which are very important for light, because light can act as a wave. So we know that the wave equation, velocity equals wavelength times frequency, applies to all waves. And what we found with visible light is the difference between different colors actually is their wavelength, and therefore also their frequency. The purple end of the rainbow has the shortest wavelengths of about 390 nanometers, which is 3.9 times 10 to the negative 7th meters. These are very short distances between wave peaks. But if you go towards the red end, the wavelengths get longer and longer and longer, and the frequencies get lower and lower and lower. So that's ultimately the physical difference between different colors of light. All light, regardless of wavelength, has the same speed, 3 times 10 to the 8th meters per second. It's a value that gets used in physics a lot. So if we know the wavelength of the light we're looking at, we can calculate a frequency in hertz. Just make sure you're using the proper units. It's meters and not nanometers. So every wavelength of light has its own frequency. Long wavelengths have low frequencies. Shorter wavelengths have higher frequencies. Now, where does light come from? It seems to be from wiggling a charge. If you have a situation where an electron or a proton or something charged moves up and down, it creates waves in space in what are called the electric and magnetic fields. We'll study that later. Now, what's important about this part is just understanding that because this is happening in space itself, in these electric and magnetic fields, light waves do not need a medium to travel in. So unlike sound, unlike mechanical waves, this can travel through empty space, which is something you already knew, because honestly, Earth gets most of its energy from the sun. If that was not possible without a medium, we would be in trouble, because there's not a huge amount of stuff between us and the sun. So it's really good this energy can be carried. These kind of random numbers for the colors of light we can see for their wavelengths and frequencies kind of beg the question, why? What is it that makes these particular wavelengths and frequencies special? And the answer is they're not special. The reason these are the colors that we can see is that these are the colors that certain receptors in our eyes are sensitive to. These colors will come in and cause charges in our eyes to start wiggling, which our brain can then pick up. But the truth is, other wavelengths and frequencies do exist. And they can go from much longer wavelengths than red all the way up to much shorter wavelengths than violet. So light is one part of something big that we call the electromagnetic spectrum. And let's look at some of the other pieces of the electromagnetic spectrum. So I'm using the visible spectrum as our reference. And if we go in one direction, in other words, longer wavelengths, lower frequencies than red light, the ones closest to red light are infrared. When you get a little bit longer wavelengths, lower frequencies, that's called microwave radiation. And longer than that, lower frequency than that, those are radio waves. So there's not a fundamental difference between radio waves and, say, blue. They're both electromagnetic radiation, and the thing that's different about them is their wavelength and frequency. If your favorite color is blue, that's awesome. If your favorite color is 98.7 WNLCFM, that's awesome too. They're both just a specific wavelength of electromagnetic radiation. So what I'd like to do now is take a look at some of these other frequencies and wavelengths of light that we can't see. We're going to start with infrared and make our way to longer and longer wavelengths. Once we do that, we'll double back and we'll start with ultraviolet and make our way to shorter and shorter wavelengths. So let's look at an example at how we use infrared light in our everyday lives. One application of infrared light is for TV remote controls to talk to TVs. You've probably noticed that there's an LED on the front of most of your remotes, but you've probably never seen it light up. You may see a tiny reaction in this film, but not very much. Turns out there is a lot of infrared light coming out of this LED, and the reason you're not seeing it is not because the phone can't see it. The electronics in the phone are actually sensitive to infrared light, unlike our eyes. This is an iPhone 6s Plus, and Apple puts a filter in to block colors of light the human eye can't see. So you may be getting a couple of glimmers, but not very much. But just to show you this infrared light, let's take a look at what it looks like through two other phones. This is a fairly old, cheap Android, the kind you'd get at a gas station for about 30 bucks. This is a nicer, more modern Android, and we'll see how much of that infrared light they let through. We'll start with the older, cheaper one. Okay, so this camera does not have any optics to block infrared light, and you can see that the phone is highly sensitive to it. Now it's looking blue-purple. That's not because infrared light has any color. Infrared light actually doesn't, by definition, since we can't see it, but it's just how the phone's electronics are interpreting it as it sends the signal to the screen. Let's take a look at the slightly more modern Android. So in this case, the light is there, but harder to see than with the one that doesn't block any of the infrared light. So at the end of the day, infrared light is very much present in communicating between a remote and a TV. You can see that this is flashing in a pattern. Pressing different buttons gives a different pattern, and that's how the TV knows what you want it to do. So there's lots of colors of light that are out there that our eyes simply can't see. That doesn't mean they're not there, and it doesn't mean we can't make use of them. Let's take a look at some of these other colors. As you go to longer and longer wavelengths, you enter what's called the microwave region of the spectrum and then the radio wave region of the spectrum. These are both really important for how we communicate wirelessly. Most things that communicate over longer distances require either a microwave signal or a radio wave signal. So what I've got here is a list of common wireless devices, just kind of lined up on my classroom floor. And I've got a laptop and an iPad. Well, they communicate over Wi-Fi, and the networks as of 2016 that were commonly in use were these standards. And that's a frequency of 2.4 gigahertz and a wavelength of about 12.5 centimeters. So using the size of the laptop as a scale, I put in what the wave peaks would look like for a Wi-Fi signal in my classroom. So again, about 12 centimeters apart from each other. Some other common wireless devices we use are FM and AM radio. Those have much longer wavelengths. Notice that AM has a significantly longer wavelength than FM. So here's a little radio. The first FM peak would be here. I guess the next one would be somewhere off here. But the AM one can't be pictured because it would be, nearly 300 meters away. AM wavelengths are very, very long. Different cell phones in different carriers in different countries use very different signals because honestly it's up to each country to allocate which colors of light you're allowed to use for any particular signal. So phones have to be built to work on a very specific standard for the country they're being used in. Or more commonly now, they have to be adaptable. Two commonly used kind of regions of the spectrum in the United States are around 850 megahertz, which is a wavelength of 35 centimeters, and then 1900 megahertz, which is about half that. So these pink and brown lines here, those correspond to the two different regions of the spectrum we use for cell phones in the United States. So they're fairly different from each other, and like I said, they're different in different countries. Walkie-talkies use a variety of frequencies. There's CB ones that use very long wavelengths. There's marine radio. The one I have here is the kind you'd buy at a Walmart for buying walkie-talkies. And they use what's called the General Mobile Radio Service. And that has a wavelength of about 65 centimeters. Again, you got to have the right walkie-talkie for the application you want so that the right set of users actually hear you. A GMRS radio is not going to pick up something on the marine channels or the CB channels. The TV channels are tucked in several places around the electromagnetic spectrum. They all have numbers in the United States, but those numbers don't really correspond to the actual wavelength and frequency the broadcast's on. There's generally two big parts, what's called the VHF, and channel 13 is an example of that. So the waves coming into this TV on channel 13 are about 1.5 meters apart. But the other part of the spectrum, the UHF, has waves that are much closer together. Now there's dividing lines in those two, and it turns out that you actually need a kind of different antenna to receive electromagnetic radiation of such different wavelengths and frequencies. Let's look at a typical TV antenna, and you'll see what I mean. So this is a typical attic mount TV antenna, and what you see here is a curved mirror, and bear with me that this is a mirror. We'll talk about that in a minute. And you've got basically these dipoles for getting the different wavelengths of light. So those really long VHF waves, this is the antenna for them. And then the shorter and shorter UHF waves each have their own antennas for different regions of the UHF, depending on how long or short their wavelengths are. So what's the point of the curved mirror? Let's take a look at something similar for visible light, and I think that will make more sense. So you can think of the radio waves as being like these parallel rays of light, and they come into the mirror, and the curved mirror reflects them and focuses them to a point where we expect the light to be very bright. Let's see what that looks like on the mirror with the TV antenna. So because of the shape of this mirror, it's not going to reflect all waves of different wavelengths to the exact same place, and that's why the different dipoles are in different places. But in general, the waves will come in and be focused onto the appropriate antenna for each wave, and then we'll get a stronger signal. Now, I think it's fair to ask, how on earth is this a mirror? And that's really tied to the question of how do all of these devices receive radio and microwave signals inside? Green light can't go through a wall or a roof. Why can FM? Why can Wi-Fi? Why can a cell phone signal? And the answer is materials interact with electromagnetic radiation of different frequencies differently. Things that we think of as opaque or transparent are only such to certain frequencies. So to radio waves, this curved object here acts as a mirror, and that's fine. We'll see that knowing whether something is opaque or transparent to a frequency is important as we get to very high frequency wavelengths as well. So as we just saw, there are physics reasons to use a specific wavelength and frequency for a specific purpose. But it's important to understand that the reason that devices are divided up to use very specific wavelengths and frequency is often also a legal thing. Basically, the electromagnetic spectrum is very valuable real estate. If all people who wanted to use devices to communicate wirelessly could just pick any wavelength and frequency, or in other words, any color of light they wanted to broadcast on, those devices could start to interfere with each other pretty quickly. So I'll give you a funny example of interference. Around 2005, people's garage door openers started going ballistic. And it turned out that the reason for this was the wavelength and frequency the transmitter in your car uses to talk to the opener. It turned out that that frequency was really close to a US military frequency. And the military hadn't used their frequency in a long time. So no one had really known that they were too close together and could interfere with each other. Sure enough, the military started using it again, and garage doors around the country went ballistic. They started jamming in certain positions. But at the end of the day, it wasn't the military that had to change, because they were the legal users of that frequency. So you can see that who's a legal user is actually a political decision. You've probably been driving in your car listening to an FM station like, say, this one, 91.7 megahertz. And as you get farther and farther away from the city it's from, it starts to fade out. And maybe another station starts to take its place. And there's probably a place where you hear both stations at the same time, and it's really hard to listen to. So to prevent that kind of interference for most people in the city listening to that station, certain radio stations buy the right exclusively to use that frequency. And it's the government's job to assign them a frequency and make sure that nearby stations don't overlap, so you get that kind of interference. So there's a pattern as you go around the country of which frequencies are used in different cities. And that's why TV and radio broadcasts in different places are all on different channels, so that each city can have its own set of channels and not interfere with adjacent cities.